Thank you.
This is the form that we're supposed to be taking yesterday, but I wasn't.
Okay. All right, do you have all your homework turned in from yesterday? Up to question 20? Go ahead and say it for everybody. In the Father, and the Son, and the Holy Spirit, amen. Our Father who art in heaven, hallowed be thy name. Thy kingdom come, thy will be done on earth as it is in heaven. Give us this day our daily bread, and forgive us our trespasses, as we forgive those who trespass against us. And lead us not into temptation, but deliver us from evil. Saint Faustina. In the name of the Father, Son, and Holy Spirit. Amen. We'll take a few notes to start off today in class, so we'll do a few experiments after that. Could y'all close the blinds when you get your inspectors? See them. So we're still on section 4.2. Finish that up today. So just a few things to cover that we didn't get to yesterday in 4.2. One thing is drag force. So when something moves through a fluid, and a fluid can be air or water, the fluid exerts a drag force on the moving object in the direction opposite its motion. So when you swim, you have to push water out of your way to move through it. And as you do that, you're pushing against the water. Friction between the water and you and the weight of the water slows you down. And that's the drag force that you're feeling. Same thing going through air. So anytime you move, you're moving through air, and you have to push the air molecules out of the way to do that. Now, they're a lot lighter than water, and so it's easier to do, but it still requires some force to push through the air. And that's drag force that you feel. So at any given moment, you have air molecules hitting your face at 1,000 miles per hour. And you have billions of them hitting all the time. But you're not aware of them when you sit still. It's only when you start to move, when you have to push them out of your way faster, that you really start to feel the effect. And that's what you feel as wind. You know, if you were to drive in a car with the open top or the windows down, the wind that you're feeling is the air being pushed out of the way as you travel through the car. So the drag force is the force exerted by a fluid on the object moving through the fluid. You already pretty much wrote that down. Don't worry about number 2, just the first bullet point. It just repeats itself. Can you see this picture? I mean, I guess you can't really read that, but like you can, like, it's a tennis ball. You're seeing 2 forces. Do you see right here that little dot? So what it's showing you is that it's 2 vectors. This is the drag force vector that goes upward, and this longer arrow downward is the force of gravity. And so when you first drop a tennis ball, the drag force is pretty small. Now, force of gravity is constant. You know, throughout here, you're going to see the same vector length for force of gravity. That's the ball's weight, and the weight does not change based on where it is in the air. But as the ball goes faster and faster, drag force increases. The vector length of the drag force gets larger and larger. There's more and more drag force as it gets faster.
The drag force is going upward, then why is the ball moving faster as the drag force is getting larger?
That's a good question. Because it's still, at this point right here and upward, there's still unbalanced forces. you still have a longer force of gravity or a larger force of gravity than you do with the drag force. And as long as the force of gravity is larger than the drag force, it will keep on accelerating. Now, when they're equal to each other, it will not accelerate anymore. And so at this point, when these equal each other, when the drag force equals the force of gravity, the ball does not get any faster. It maintains its speed at that point. But until that point, now it won't accelerate as quickly, but it will still pick up speed. As long as the drag force is less than the force of gravity, it will still pick up speed. It's only when they are balanced that you would have no more acceleration or no additional velocity change. Now at this point, it's called terminal velocity, when the drag force is equal to the force of gravity. So as it drops in this ball, its velocity increases, so does the drag force. And then when it gets to the point where the drag force equals the force of gravity, you reach terminal velocity, and it won't get any faster at that point. Yes.
The drag force won't get any faster, or the velocity?
Oh, the velocity won't get any faster.
Okay.
The drag force will also maintain constant. At that point, it's a constant speed, so constant drag force at that point.
Okay.
For a human, it's about 9 stories of a drop before you reach terminal velocity, which means that you could jump from 9 stories or jump from 100 stories, and you reach the same speed, and you won't get any faster at that point. And that's about 200 miles per hour for a human. 125 if you're really spreading out, but 200 miles per hour if you're more like, straight up and down.
So I've heard that like if you drop a penny off the Empire State Building, it could kill someone. Is that?
Yeah, I mean, that's almost a myth. I mean, it's possible it could happen, but you only will get a slight bruise. If you were to have a penny hit your head, at most it'll be a slight bruise. Now that bruise possibly could cause internal bleeding, or you could jerk your head back and pop a blood vessel. I mean, those things that could happen, but on its own, the penny won't be fast enough to cause really a severe injury. It'll be like a paintball injury. I mean, that's what you're going to feel. It's like a paintball hitting you. So it would not be a significant injury usually, but a paintball could potentially kill you. I mean, that's a possibility. Is it likely? No, but it's a possibility that it could hit you in the right way, and that you could die from it, but it's pretty unlikely that would happen. So same thing there. Some animals have a low terminal velocity, like cats can jump from any height, and usually they're going to survive that height because their terminal velocity is about 60 miles per hour. So if they jump from a 9-story building, 100-story building, they will hit the ground at the same speed, 60 miles per hour, which they can usually survive just fine. They don't always, but they usually survive any height that they drop from, because it's not a significant speed they're hitting the ground with. I mean, they don't like it. I mean, it's not comfortable to hit the ground, but they can survive that drop. Small animals like gerbils and hamsters have a very low terminal velocity too, and they don't usually get injured from dropping from any height. Now, they can die from shock though. So hamsters, gerbils don't like dropping, and they can be really scared and have heart attack, but they wouldn't die from injuries usually when they fall, because they fall at a very low speed. Chickens also, same thing. They fall at a very low speed. Yes.
So you could throw a cat out of a plane and it would die.
Yeah, I mean, it usually would not. Now it could break a leg, and it might die from shock. I mean, it wouldn't like it, and so it might really be terrified of what happened, and it could die from just being so scared. But it wouldn't die from injuries usually. Now, is it guaranteed? No, but usually they don't die from high falls. And I think that's why they had the expression cats have 9 lives, because they would see cats fall from really high heights and think, well, that should have killed the cat, and it didn't. But it's because they hit the ground at a low speed. For a parachute, it's about 11 miles per hour. So you hit the ground about 11 miles per hour with a parachute. But if you don't have a parachute, it's about 200 miles per hour when you hit the ground.
Oh, so how fast do you get if you jump like 20 feet?
20 feet?
Like jump from a 20-foot edge or something?
Yeah, I'm not sure about 20 feet. You wouldn't reach terminal velocity, that's for sure. That would probably be, I can check in a second. I can figure that out. Just remind me, I can figure that out for y'all. I mean, definitely you could break legs at that height. You know, definitely, I mean, if you don't hit the ground in the right way, you could certainly hurt yourself. It's enough to hurt, to break bones. Let me see. On this slide right here, so it says that you have the mass of a person on Earth 20 kilograms. What will his mass be on the moon? Gravity on the moon is 6 times less than Earth's gravity. So, oh, sorry, I went too far. No, I can't get back to it probably. Mass does not change. That's the point of this example, is that mass is constant no matter where you are, whether you're on Earth or the moon. Weight will change, but mass is constant. So 20 kilogram mass on Earth will be the same on the moon because mass is not tied to gravity. It's tied to how much matter you have, which will remain constant. Okay, and this one, your mass is 100 kilograms. You're standing on a bathroom scale in an elevator. What is the scale reading when the elevator is in free fall? So in free fall, remember, you weigh nothing. So the weight would be 0. You can't push down the scale, it can't push up on you, and so your weight is 0 in free fall. Okay, last question on here. In which of the following cases will your apparent weight be greater than your real weight? Do you remember this one? Which of these look like the one that would make you have a greater apparent weight than your real weight? This elevator at rest, accelerating upward, accelerating downward, or false none of the above? Will?
I would be accelerating upward.
Good, exactly. So if you're moving upward, you will feel heavier than when you're at rest. Let's see. I think that was the last question on here. Let me check to make sure. Okay. So we'll stop here. Now, there's a few things I want to do. If you go into your book on page 103, there's a mini lab I want you to do. Find the mini lab on page 103. Let's go through that.